We'll get started. So it's my pleasure to introduce Bai Cui, who's an assistant professor at Iowa State University. So Bai was at Michigan over 10 years ago as a student in the joint Shanghai Jiaotong University of Michigan program. So he has a bachelor's degree from the University of Michigan, and then he went to Georgia Tech where he did his PhD, and he was at Argonne National Lab and Edwell for a number of years. Now he's just started as an assistant professor at Iowa State. So the floor is yours. Thank you.
Thank you, Johanna, and thank you, everyone. It's really nice to be back. I think I haven't been in Ann Arbor for 10 years. Last time I was here, it was 2014 when I watched the Manchester United versus Real Madrid game here. So that's the last time I was here. So it's really very grateful for Johanna and everybody for your hospitality and have the chance to come back. So it feels to be home again. So it's really nice, and have the great honor to be presenting here today. Like Johanna just said, I just joined Iowa State last fall. So I'm mainly working on power systems. I've been working on a number of power system problems. When I started my PhD, I was working on bulk power system voltage collapse problems. I worked on some OPF power flow problems for a while, and I also work on some distribution system problems, for instance, network reconfiguration problems, and so on. And while working at NREL before I joined Iowa State, I started to look into this DER integration problems. How can DERs be integrated into the bulk power system? How can they be aggregated? So that's the topic that I've been working on for a couple of years now, and also the topic I'm going to present today. So topic of my presentation is great integration of distributed energy resources. I'm going to talk about two topics. One is their aggregate flexibility quantification. The other is their market participation. So how do they integrate into the market? So as we all know, we're transitioning from the power system is undergoing a paradigm shift. It's going from a passive system with mostly synchronous generator towards a system with more renewables, which means we have less synchronous generators. We have less of those big coal power plants. We have more distributed energy resources. We also have a massive DER and controllable loads. So this is both a blessing and also, I could say, a curse, because it brings a lot of problems, but also allows us with a lot of flexibilities in how we exploit those devices to our benefit. And in this talk, I'm going to talk about how we can harness those distributed energy resources, mainly quantifications of their capabilities and integration of their capabilities into the bulk power systems. So the overarching structure of the problem I'm thinking about is, we have a hierarchical DER management system. So as we can see from this figure on the right, we have a feeder, right? And at the very bottom level, where we have the individual customers, we have this whole management system or demand response programs, where we have controllers that controls each individual house. We call this the edge, grid edge management systems. They basically manage, measures, and controls each end user. And then those end users, they are aggregated by some community aggregator. And those aggregators, they're trying to aggregate a number of end users and trying to bring those devices to the bulk power system. Of course, in doing that, we also have to respect some distribution system constraints, because the aggregators normally they don't have visibility into the distribution system. They have no observability, and they also have no responsibility in managing the reliability and also the stability of the distribution system. So we also need certain distribution utility to help manage or set certain bounds for how those aggregators should manage their end devices. And this is mainly the basic setup that we're trying to trying to leverage here. And then this problem, we identify 3 problems. First is we want to identify for each aggregator, we call this aggregated solar and other DERs etcetera. For each of this aggregated devices, when they participate into the wholesale market, when they participate in this capacity market, they need to submit their cost curve. Basically, they need to submit for MISO system, for instance, up to 10 pairs of price and quantity. So for given market current price, how much quantity, how much power they're willing to offer to the bulk power system. That's something that we have to come up for those aggregated devices. Of course, for large conventional generators, they also have to do the same thing. But for them, they have been in this industry for decades. They have very good understanding of their price quantity relationship. They understand very well their fuel cost, and that's mainly something that determines how much power they want to offer given each market current price. But for this aggregated devices, since their marginal cost is very small, their cost is mainly the operation cost. So how do we leverage their flexibility in different modes of control to use it to our benefit to best find the price offering pairs to maximize the aggregator's profit? That's one thing we're trying to solve. That is shown here as the piecewise staircase curve here that just captures the price quantity pair they're going to offer to the system for scheduling. And also something that we also need to quantify is what is their power generation capability, right? So we have a lot of devices in the distribution system. Of course, we have a very good understanding of each individual device, right? For PV, we have forecast. For demand response resources, we know their shifting or their load shedding capability. But when we aggregate them, what is their aggregated capability in generating power, considering uncertainties and also considering distribution system constraints? That is something, as we will see, is not very trivial to determine. And that's also something that we have to figure out when we are trying to integrate them into the market. So that's the second problem of characterizing this aggregate flexibility of aggregated DRs. And the third part is, once we submit those characterization of this aggregated DRs, we receive the dispatch signal. How do we disaggregate them? How do we do real-time control to realize those dispatch signal in the most economic way? So those are the 3 problems that we're trying to address in this whole scheme of DER integration problem. In this talk, I'm going to focus on the first 2 parts of this problem. So the outline of my talk can be characterized into these 2 parts. First, I'm going to talk about the aggregate flexibility calculation of DERs, and then I'm going to talk about the optimal offering strategy for aggregated DERs. I'm not going to talk about the real-time disaggregation part. And so let's jump into the first part, which is how to characterize aggregate flexibility. So as we all know that the distribution system is transitioning from a passive element where you just have passive load into a more active virtual power plant, which means you can have active control to realize their generation capabilities to be integrated as a player in this bulk power system to provide great service, to bid into the energy market, to bid into the capacity market and also ancillary market. As you can see from here, we have very good understanding of the TSO and DSO, the transmission system operator and distribution system operator interaction. But we don't have really good understanding of how the microgrid operator work with distribution system operator. We don't have good understanding of how the distribution system operator works with aggregator or this VPP virtual power plant. And we actually right now don't have a connection from the aggregator or the VPP to the wholesale market. That is something that FERC Order 2222 mandates, but it still takes some time for different ISOs or RTOs to come up with their compliance plan to really integrate those DERs into their market. So the compliance plan that those ISOs have to come up with in the first order, it requires that aggregated DERs or even a single DER larger than 100 kilowatt cannot be banned from integration into the system. So it has to be allowed to be able to integrate into the system for any aggregated DERs larger than 100 kilowatts. Of course, the level of adoption of this order varies in different areas. Some areas in the US are more active in pursuing this. Some areas are less so, but I think we're all moving in that direction. And in the question we're going to ask is, as a virtual power plant, what is the generation capability or the power potential of providing the grid service by those distributed energy resources if we have good understanding of both the individual device and also their network models? And how do we effectively integrate those DERs in the power system, in the wholesale market, accounting for the network constraints and also accounting for uncertainties that we have? So we talk about aggregate flexibility. Okay, what is aggregate flexibility? So aggregate flexibility is the power generation shaping capability of a collection of heterogeneous DERs located on a feeder or geographically distributed across multiple feeders over several hours to a day. So we often think about this aggregate flexibility as some DERs integrated, located in the same feeder, but that's not necessarily the case. The first quarter 22 also explicitly allows aggregators that controls DERs from different pricing nodes to be integrated into the market. So those DERs can be located in the same feeder, or they can be located in different feeders or even different points of common coupling to the transmission system. And we want to quantify their generating shaping capabilities in this case. And as we can see from the figure on the right, this aggregate flexibility is something what we're talking about. For those different kinds of devices, maybe you have a rooftop solar, maybe you have electric vehicle, maybe you have some energy storage devices. Their energy generation capabilities. At time T1 and T2, how much power you can control for them to generate. But how do you quantify their aggregated flexibility at this point? For instance, if all of the batteries, they're discharging, maybe it goes beyond the hosting capacity of the distribution system, right? Maybe you will have some under voltage problems, right? You cannot discharge all of the batteries at the same time. Then how do you quantify, how much aggregate flexibility you have at the feeder head, at the point of common coupling between the distribution system and transmission system? That's something we're trying to quantify. Another point we're trying to address is we can see that what we're really trying to characterize is a time-dependent, a time-coupled flexibility. It's not a flexibility where you characterize this flexibility for a single time period, right? You have this lower bound and upper bound, and you say, okay, this aggregate flexibility has to be within this lower and upper bound. What you're really trying to characterize is a multi-time period, time-coupled flexibility, where if you generate more, maybe you don't have that generation capability for the next time period. We're talking about, for instance, energy storage, right? If you discharge in this time period, you can't discharge. If you deplete your battery in this time period, you can't discharge anymore in the next time period. And for some of the shiftable load, right? If you shift it to some later period, you have certain constraints in later period that you have to satisfy. So it's all time coupled, and that brings some computational challenge to this problem. So that's our basic setting. Okay, so we want to distinguish between two types of flexibilities. One is at the device level, right? We have uncertainty, we have the controllability. We can quantify the flexibility at each device level. For each, for instance, rooftop solar, for each building, for each EV, how much flexibility they have. That's something we assume that we already have a good understanding of. And we want to quantify, what we want to quantify in this work is at this asset level, at this aggregated solar and other DR level of flexibility. If we have some uncertainty of uncontrollable devices, we have the flexibility of each controllable load or controllable device. And we also have the network constraints. How do we combine them all together and come up with the flexibility, the aggregate flexibility? That's the problem we're trying to address here. Okay. So really, what we're trying to do is to enable asset to build into energy and capacity market with their power generation characteristics. And something we want to guarantee along the way is that for any power offering that we can quantify here, we're able to make sure that under any uncertainty realization, we can disaggregate them, we can control them, we can dispatch them through a certain control of the DERs without the violation of any distribution system constraints. So that means we take into both distribution system constraints into account and also the uncertainties into account when we do that. We see that we're dealing with three kinds of DERs in this study. We have some energy storage modeled, we have some HVAC, also have PV inverter. And we see for both the energy storage and HVAC system, they have some uncoupling constraints. For energy storage, of course, we have the state of charge constraint. And for HVAC, their temperature is also time coupled, and the required temperatures that we have for this period and how much power we need is coupled through the previous time step in terms of the indoor temperature and ambient temperature. So of course, additional devices can be included, such as some shiftable loads and also EVs and so on. But I think we are the method itself is general enough to accommodate different models. And notice we're dealing with a linear set of equations in this case. Okay, so here's a model we're working with. At the device level, we have three kinds of DRs. We have energy storage units, we have PV inverters, we have HVAC system. And we also have a network model that captures network constraints. In this case, we're using a linearized power flow model, which, as we can see from the first equation here, relates the real and reactive power generated at each device to the voltage. So the voltage and the power output, they have a linear relationship here. This is commonly used for distribution system modeling. So a variant of this Lindy's flow model that is widely used in distribution system analysis. And the constraints we impose is that the voltage has to be within lower and upper bounds. For distribution system, this is normally tightly regulated voltage constraints. You cannot go beyond, for instance, a few percentage of the voltage deviation from the per unit value. Beyond those two constraints, this constraints captures what is the relationship between the generation of each individual device, which are PQ delta and PQY. They're delta and Y connections of the devices in the network, to the aggregate flexibility, this P naught. This P naught is what we care about. This is what we call the aggregate flexibility, the aggregate power generation capability, and that we want to quantify in this work. So if we put this network constraints and also the device constraints together, we come up with this compact model with uncertainty, right? For this first set of constraints, think of plugging everything in here, the right-hand side of this constraint into the V. Then we have a constraint on the power injection, right? And also plug in the device model in here. This first set of inequality constraints really captures the flexibility of each device constrained by their individual characteristics, as well as the network constraints. The voltage constraint is captured in here, and also the device their device models are incorporated in this constraint. And we have this eta here that quantifies the uncertainty of some uncontrollable loads in here. So we want to make sure that for any uncertainty realization, we can find a P that this constraint holds, which means for any uncertainty realization, we can find a DER dispatch signal that respect their individual constraint as well as the network constraints. Okay, something we're trying to characterize is this P naught equal to P, D times P, this mapping from individual device power output to the aggregate power output. Okay, so we'll have this model at our disposal. Our goal, formulated mathematically, is with full controllability of DERs downstream. That is, we have full controllability of this P. This P can vary within this feasible region characterized by this inequality constraint. All we're trying to do is we want to derive the aggregate power flexibility. We want to derive what is the image of this alpha mapping from P to P naught. That satisfies that for any uncertainty realization, we can find a P that satisfies the set of equations. And we have different way of characterizing this general geometric region or doing inner approximation of the general geometric region of P naught, right? When there's no time coupling, right? Something we can do maybe is this the square is the actual flexibility region, right? If we do a hyperbox approximation, right? If we quantify what is the upper and lower bound of the power generation capability in each time period, we quantify this red region. Maybe this red region captures the actual aggregate flexibility region really well. And if we do ellipsoidal inner approximation, this inscribing circle or ellipsoid, maybe it doesn't capture the flexibility as well as a rectangle when there's no time coupling, right? When there's no time coupling, meaning that the flexibility in one time period is not affected by the flexibility in another time period. But but we know from this, intuitively, from this aggregated device characteristics, there's time coupling. So the flexibility you have in time instant 1 will affect your flexibility in time instant 2. So what we end up having is a flexibility region that is shifted, that is not a coordinated aligned square. In this case, if we use a coordinated aligned hyperbox to inner approximate this aggregate flexibility region, maybe we don't get as good as a result as we can for using an ellipsoidal inner approximation. So that is something we're shooting for. We're trying to capture as much as possible of this uncoupled aggregate flexibility region. That's why we opt for this ellipsoidal inner approximation. However, finding this maximum volume inscribed ellipsoid in a polytopic projection, that's what the problem that we have at hand. It's not easy. It's actually an NP-hard problem. And also, if we just naively taking the maximum point and minimum point when we try to solve this optimization problem, you maximize your aggregate flexibility, you minimize your aggregate flexibility, you find those 2 points. That actually doesn't work. That doesn't give you the aggregate flexibility region. For instance, in this case, you find this maximum point here. This is P naught bar and P naught under bar. You find these 2 points. From this linear programming problem, we can guarantee that anything between the convex combination of those 2 points that we find will be inside this feasible region. But it doesn't imply this whole square satisfies this flexibility constraint, satisfy all the constraints. So it only guarantees the convex combination of those 2 points that satisfies this constraint. If we really want to get a good characterization of this flexibility region, we have to make sure all the vertices are within this flexibility region, not just the maximum and minimum, not just a subset of those vertices. what I'm trying to say. So in this case, it becomes a very computationally expensive problem because you have to make sure all your vertices are within this flexibility region. And that also leads to some conservativeness. So what we do is we want to, go beyond this approach and identify this maximum volume inscribing ellipsoid. What we mean is we want to find this ellipsoid E that's parameterized by this parameter C. We want to find this positive semi-definite matrix E and also this vector E, such that for any point in this ellipsoid and for any uncertainty realization within this uncertainty set we characterize, there exists a P, an individual DR dispatch signal that satisfies those inequality constraints. So we can formulate this problem into this kind of robust optimization problem, where we want to maximize this log determinant of this E, which is the proportional to the volume of this ellipsoid, such that for any point in this ellipsoid and for any uncertainty realization, there should exist a DR, individual DR dispatch signal that that maps to this aggregate flexibility, and also this disaggregation strategy, this DR dispatch signal satisfies all the inequality constraints. So that's the goal here. We can do a little bit of reformulation to reformulate this equality constraint to an inequality constraint into this following form, because robust optimization involving this kind of equality constraints is really hard to deal with. So we do a little bit of linear algebra to reformulate this linear constraint into this equality constraints into inequality constraints. We end up having this kind of robust optimization problem here. And we know for this problem is it's not very easy to solve. It's adaptive robust optimization it's not tractable to solve, because we want to make sure that for any uncertainty realization, there exists a second stage variable that satisfies all the constraints. And a common way to do that, to reformulate or approximate it, is through some second stage, some affine policies relating the second stage variables to the first stage decision variable. So we tried two policies, both quadratic policy and affine policy, where we relate the second stage decision variable, called this, eta, which is collection of both the parameterization of the ellipsoid and also the uncertainty. We relate this second stage variable to our first stage variable y, or this first stage variable to the second stage variable y. And for this affine policy, we just have this affine relationship between the second stage variable and the first stage variable. Yes.
Question. I see that here you make an assumption on the policy, if it's a quadratic or affine policy, right?
Yes.
But do you have any data that would confirm what is the optimal policy in fact?
Yeah, that's a great question. That's something I'm trying to get into, because it seems like with quadratic policy, you really get this affine policy as a special case, right? Because when you take Q to be a zero matrix, and that just becomes an affine policy. So just by looking at the two policies, you see that this quadratic policy should always outperform this affine policy. Of course, there is some computational difficulty with this quadratic policy, but an interesting part of this is that there is more nuance to it, because for this affine policy, as we mentioned, this admits an exact SOCP relaxation, reformulation. So this reformulation is exact, it becomes a tractable problem. Whereas for this quadratic policy problem, even though it seems more powerful, right? It seems as just dominates this affine policy, we see that we don't actually have a tractable reformulation. We only have an SDP inner approximation with certain tightness factor. And what that end up having is that the two formulations, the two reformulations or approximations, they're actually incomparable. And we will also see that from some of the simulation results that we have. But yeah, that's a great question. Thank you. So yes.
The quadratic policy you can do, you're doing a relaxation, as I understand with the SDV.
Yeah.
But could you solve the affine policy, which you're saying you can solve to optimality, and then use that as an initial seed for like a non-convex optimization with the quadratic policy?
Right. Yeah, that's a great point. I haven't tried that, but yeah, maybe that's something we can we can definitely try out. Because solving this SDP in approximation is already a very challenging problem in itself. So yeah, I would assume we could run into some additional problems with that. But I think in terms of the quality of the solution, I think that's a great suggestion. Yes, we could definitely try that.
Other versions or variants of the problem where there's an exact solution. You said if I restrict myself to class of affine policies, then there is a globally like a tractable global optimization.
Yeah. You mean other policies?
Just in the general formulation, if I make restrictions on the types of data, like if I was looking at, if you were looking at a distribution network and it was a star network or something very simple, are there special cases where you get exact solutions?
I'm not exactly sure. I think we're working with a fairly general set of equations. We're not actually exploiting the structure of the distribution system. But yeah, maybe there's something to look into, but I'm not exactly sure. Yeah. Any other questions? Okay. So yeah, here are the two formulations. We can see with this quadratic policy-based approximation, we end up having this, SDP problem. We have this maximum log determinant problem with some SDP constraints. This is the approximation. Whereas with this affine policy-based approximation, we have this exact SOCP formulation here. So the takeaway is the quality of two approximations are actually incomparable. So we can actually find a case. We can construct an artificial case where this affine policy is strictly better than this quadratic policy. So yeah, and that's something we can see empirically from the simulation results. So here's what we use to test our aggregate flexibility result. We are using this Southern California Edison 126 node three-phase distribution system feeder. As we can see, different colors mean different phases. The blue lines, the blue dots, I assume they are three-phase loads, and with different shades of red and pink, we have two-phase and single-phase loads. So this is a three-phase unbalanced system, and we put a number of different DRs in the network. We have 24 energy storage units, 33 PV inverters, and 5 HVAC system in the system. And we run this aggregate flexibility characterization for 4 time periods, and we get this 4-dimensional ellipsoid to characterize their aggregate flexibility. Of course, we can draw a 4-dimensional ellipsoid here, so we project them onto 3 2D planes here. This solid red ellipsoid shows the ellipsoid in our approximation using this quadratic policy, and the dashed ellipsoid here shows the affine policy. So as we can see, somewhere maybe around here and over here, we see that at a certain point, this affine policy outperforms a little bit of this quadratic policy, which verifies our theoretical observation that they're comparable. But in general, this quadratic policy is able to characterize a larger volume than the ellipsoid using affine policy, as it should be expected. And both of them outperforms this original hyperbox approximation that we used. So here's the simulation results. And so any question up to this point? Yes.
Do you only consider coupling between only 2 time steps, or is there any possibility of extension to considering coupling between multiple timestamps?
Yes, that's a very good question. Yes, for the current modeling, we're only considering 2 time steps because the energy storage and also the HVAC, the way we model them are only coupled within this adjacent 2 time periods. But like I mentioned, if we have shiftable loads, right, we can definitely have a coupling of multiple time period, even maybe the whole day, right? We can have that kind of coupling, and this model can be incorporated in the general analytical framework, but we're not modeling that. Yes.
Is it scalable to consider like over 3 timestamps? How much timestamps?
Yes. So for this IFM policy case, I think this SOCP is quite scalable. But for the quadratic policy, since we're solving a large SDP problem, it's not really scalable. So we are so solving a 4-stage problem takes about half an hour, but solving problem with more time steps takes significantly longer time. So the scalability is an issue that we're trying to address here. Yeah. Yes.
At the beginning, you mentioned that you use linearized power flow.
Yes.
Have you checked whether if you use the full power flow equations, whether the solutions you get maybe are infeasible or they violate some constraints?
Yeah, that's a great question. I think the quality of the linearized power flow equation is fairly good. The main reason is because we have tight bound of this voltage constraint. So this voltage constraint, we have maybe plus minus 5%. So within this range, this linear approximation works really well. Maybe for larger variation of the power and voltage, we will enter this nonlinear region of the power flow equations. But within this tight bound of the voltage, this linear approximation works really well. So we haven't done the study ourselves, but I think I've seen some other papers that use this method as benchmark. I think we're able to capture around 80% of the actual flexibility region. So using actual power flow solvers. Any other questions? Yeah, Johanna.
I have a question, but I'm wondering if she can come at the end. I'll save it for the end.
Okay. All right. Yeah. So something we're currently working on is we're considering incorporating network reconfiguration. Right. We know that for a fixed network topology, we can characterize the aggregate flexibility. But something we're interested in knowing is once if we have a large distribution network, if we can do network reconfiguration, can we reconfigure the network such that we can improve this aggregate flexibility, right? And how much flexibility gain, aggregate flexibility gain, can we get by reconfiguration of the distribution network? That's something we're interested in and we are currently working on. So not a lot of results, but it's just a thought to put here. We're also aware of the challenge of doing switching in normal operation, right? Distribution systems are not normally reconfigured frequently. The most common use case of reconfiguration is for service restoration. That's when you have to reconfigure the system. Other cases, for instance, you have to do maintenance where you have strongly unbalanced in your 3-phase system. You probably sometimes do phase balancing by doing network reconfiguration, but those are the only cases where you can do network reconfiguration. So something we're curious in understanding is how much flexibility you can gain by doing reconfiguration. Maybe something you do after service restoration, right? Instead of just restoring service as much as possible to customers, you can also do aggregate flexibility improvement along the way. And maybe something we need to look into is how much benefit we get to justify this kind of approach. But some positive we see in terms of the formulation is that incorporating network reconfiguration is really not changing the tractability of this problem significantly. If we look at this top formulation where, for simplicity, we're just talking about the maximization of the hyperbox approximation, where we want to make sure that we maximize this hyperbox such that for any point in this hyperbox, we have an existing, we have a disaggregation strategy, P, that ensures network is feasible. And when we incorporate network constraints in this problem, we see that we introduce some binary variable here, gamma, that determines whether this network is real or not. And that constraints really only appears in this subproblem here. So when we do this reformulation of this adaptive robust optimization problem, we can still arrive at the same reformulation. We can still apply the same standard column and constraint generation algorithm, even when we include a reconfiguration in this flexibility problem. So that's one bright spot we identify in this problem. But of course, there's more work to be done, and this is still very preliminary, it's something we're working on right now. So okay, now I think I'm ready to dive into this second problem, where we want to determine the optimal offering strategy for aggregated DERs. So the overall idea is we want to determine the optimal price and power offering pairs of an aggregated DERs to offer into this wholesale market. We're deriving a stochastic multi-stage optimization formulation that maximizes this revenue from power offering, right? By maximizing the revenue of power offering, we mean we want to offer for the given price as much power as possible. So we get this revenue, which is the product of the price and the power offering. At the same time, we want to minimize the retail market cost with given power offering. You could have different business models with how you remunerate your DR dispatch with your customer. For instance, you can have a fixed rate, or you can have a time of use or real-time pricing for this lower level trading of between customer and aggregator. And we want to make sure that we minimize this retail market cost when we are given the power offering that we fix. And we solve this problem using a two-level solution algorithm based on stochastic dual dynamic programming. So the basic idea is for a conventional generator, right? Coming up with this power offering is straightforward. They have years of experience integrating the network. They know, how much power to offer for a given price. But for this virtual power plant, we want to offer this price. We want to offer this power for a given price. It's not as straightforward because we have different ways of controlling our devices to realize the same power offering. So the notion of the cost of certain power offering is not well defined for the system. And also your operation costs at certain period may also impact your operating cost at later time stage, right? If you delete your battery, you may have to buy it from the local market using maybe a higher price in the future state. So maybe you want to determine that when you are trying to offer your power to the market. So there's a lot of consideration of how you want to minimize your operation costs or your operation costs in this distribution system with the same power offering. So the differences between the conventional and virtual power plants is we have, for conventional power plant, we have a deterministic power generation cost. For a virtual power plant, it's really a stochastic generation cost. We have some uncertainties. We also have some flexibility. And this flexibility of DR dispatch in real-time operation under given market clearing signal, right? For conventional generator, this is fixed, how you dispatch. For aggregated DRs, this is not fixed. You have a lot of flexibility in choosing how you dispatch your different DRs in real-time operation. And also, like I mentioned, different offering strategies you should also consider future price uncertainties when you do, for instance, energy arbitrage, right? You could charge when the price is low and discharge when the price is high. So when you do the power offering strategy, you should also consider the future price uncertainty. And there's an additional layer of modeling and optimization layer to determine what is the optimal offering strategy for a virtual power plant. So a very simple, market clearing structure is as follows. We submit for both the traditional generator and the virtual power plant. We submit the price quantity pairs, right? This power quantity pair that we submit, and this demand curve, this intersection is what is the clearing offer, the cleared price, right? And this power is something that we were cleared and we're committed to provide in this wholesale market. And we want to make sure that whatever this price is cleared at that point, our offering should maximize the profit of the aggregated DERs. So as we mentioned in this real-time operation for the fixed for the conventional generator, the total cost is fixed. Whereas for this DER, aggregated DER, the total cost is not fixed and can be optimized based on different aggregation strategies. So what we are really dealing with is we're considering Markovian price model. For instance, we can have, a discrete Markovian description of the price at each time step, right? We can, for instance, have 5 price in time step 1, 5 price in time step 2, and they have certain transition probabilities going from one price to another. And we want to determine for each price, what is the optimal power offering that we should provide to make sure that when we provide this price, when the market is cleared, we are able to minimize our operation cost based on the power offering that we generate. So we have a 2-level problem. In the first level problem, we want to determine for the given price based on the Markovian price model, what is the power offering that we want to come up with. And for this problem, it is actually quite a scalable problem because we have finite number of prices, right? For instance, we have a 10-stage problem. For each stage, we have 5 discrete price signals, price forecast. We have 50 price and 50 power offering to determine for those 50 prices. However, for this DER operation optimization problem, it's really not very scalable because we have this curse of dimensionality problem, because we have exponential number of scenarios when we think about the potential realization of the clearing, right? We have an exponential number of scenarios, exponential in the number of stages to determine, and we want to make sure that our DER operation, the cost of the DER optimization operation is minimized for those exponential number of scenarios. So that is something that we want to take into account and we want to address using a stochastic geodynamic programming. So the general approach we have is here, we want to model this VPP offering strategy by this kind of optimization problem, where we want to maximize this FX, which is the revenue we get from offering power. This is in explicit form, this is just the price times power offering, right? This is something we want to maximize. Something we want to minimize is that the operation cost, given our X, given the power offering that we determine in the first stage. So we want to maximize this difference, the difference between the revenue and our cost, right? This is the difference is the profit we get. So we want to maximize this power offering such that this difference between the revenue we get and the cost incurred is minimized. And we have a second stage problem because for each of the X that we determine, for each of the power offering we determine in the first stage, we want to characterize what is the minimum cost, right? So this optimization problem in itself is a stochastic is a multi-stage stochastic programming problem, where we're trying to optimize our operation cost based on the offering. And so this problem becomes hard to solve due to this kind of 2-level structure. But the solution formulation we come up with is we have a two-stage, we have a virtual state, and we have the other stages. So in this virtual state, we are capturing what is the optimal power offering. Right? Once we determine what the optimal power offering is, then for each of the circle, which is the Markov price realization that we have, we transfer the price or the power offering we obtained by maximizing that fx and to each price. And then given this power offering, we solve this minimization problem to find this optimal cost. And we iterate between the two levels. Yes, Johanna.
So the price scenarios, it's exogenous changes, right? Like
yes.
There's no endogenous. So you assume it's a price taker.
Yes. We assume it's a price taker. Yeah, that's a very good observation. Yes. So to be more specific, the full formulation we have here is in the first stage, in the virtual stage, we're trying to optimize the revenue we get by maximizing this expected profit we get from the product of the price and power offering. And then in this stage 1 all the way to stage 24, if you consider a day-ahead problem, you really want to minimize your nested or expected cost to go given this power offering. And yeah, this whole problem can be viewed as a two-level problem, where in the first level, you solve this maximization problem. And once this power offering is fixed, you solve this multi-stage stochastic optimization problem here. To be more specific, what we have is we have a maximization problem of that first stage or virtual stage problem, and this expected cost to go function. And this expected cost to go function has a cost at a given stage plus the cost to go function at the next stage, right? So this cost here, we capture three kinds of operation cost: the cost induced by the battery, charging and discharging, the cost of operating this distributed generator, and also the cost of demand response or the demand curtailment. And it's subject to a set of constraints in the distribution system that we model, that we want to make sure that whatever power offering we have certain ways of realizing that power offering by operating our distribution system in the most economic way. So like we mentioned, the way we solve this problem is really in stage 0, where the virtual stage, we determine the power offering corresponding to different price realizations. We maximize that price offering. We pass those power offerings to different price nodes. And for this problem, we solve this DER dispatch problem to minimize the operation cost. And we iterate to minimize the difference between the revenue and also the cost. So this is the iteration process we have. In this multi-stage stochastic optimization problem, we solve an SDDP to find what is the minimum cost. And in this zeroth order problem, since we know this given a power offering, this SDDP problem is a piecewise linear, it's a convex piecewise linear function. We use zeroth order method to find an improving direction, to find a gradient of this function, the cost to go function. And we use this as a update of our price offering, of our power offering in this zeroth order problem, in this virtual stage problem. And we iterate between the two to improve our approximation of the power offering. And here are some simulation results. We apply this problem to a day-ahead market clearing problem. We consider a 15-bus power network with 14 loads, 6 distributed generators, and 2 batteries. And DR uncertainties are not considered in here. As you can see, here are the cost curves that we come up with. We have 5 prices for each time step. So there are 5 points, or 4 or 5 points for each time step. Those are the power offerings that we determine to be optimal for each time step. And we can see that when the price is relatively high, for instance, in this time slot 18, where the price, I'm not sure if you can see this, but when this price is higher, we also see a correspondence of a discharging of the battery there. There's a dip right around there before time slot 18 that corresponds to this higher price. So this VPP sees a chance of making higher profit by discharging at that point, and we also see a similar scenario at around times slot 12 and 13 when this price is also relatively high compared to other time steps. So we see a discharging there. So it does seem that this optimization problem takes into account the different prices and how we leverage this price to do energy arbitrage in deriving a better power offering strategy. And we see that this algorithm converges roughly around 20 stages. Of course, since we are doing a zeroth order method, we don't really have the gradient information. We see this fluctuation of the optimal cost function, but it converges around 200 iterations. So as a summary, we have talked about two problems. We have talked about new development in the characterization of aggregate flexibility region of DERs. We also talk about some new developments of the optimal offering strategy of aggregated DERs of market integration. And very happy to share this results with you. And I think that's all my presentation. Thank you very much.
Yes. Maybe for the question we were asking for. It's about the first part of your talk.
Yes.
You were showing us that the flexibility region of a DR reduces by adding second time component, right? By coupling two subsequent periods. But then I would understand if you add the third one, and the fourth and the fifth, the flexibility region of DR will further reduce, right? Because of the time coupling.
Yes.
Infinite horizon. For time coupling, because the infinite horizon, is there some minimum amount of flexibility for each DR that can be computed or estimated?
Yeah, I'm not sure of the asymptotic behavior of this when you take the number of stages to infinity. I would assume you will still have some finite flexibility region in that case, but I think it does shrink the flexibility region to some extent, because the flexibility you require in later stages will limit your flexibility in earlier stages. So yeah, I would say maybe it's wise to choose number of stages wisely tailored for your application. For instance, if you're doing some real-time dispatch problem, for instance, if you're doing bidding to the real-time market where you bid for the next hour with a 5-minute interval, maybe you just do this 12 time step interval of the flexibility quantification. And for different applications, you do.
But you need to do computation every time you formulate your bid, right?
Yes.
If you would have some nominal level of flexibility that is available, so perhaps maybe simplify the problem of DR participation in the market.
You have some nominal flexibility.
Yeah, the region that is always there.
Yes. Yeah, the region is dependent on different loading conditions and different uncertainty set you have. But I would imagine there to be, intersection of different flexibility regions for different parameters, right? And maybe that's something you refer to as the base case flexibility region that maybe we can use regardless of the uncertainties. I think, yeah, that's a good point. Yes, thank you. Any other questions?
The question I was going to ask before is,
the approach that you're taking is sort of top down, like you're saying, how much total flexibility is there, and then how do I access it, and then potentially later disaggregate control signals. Could you start instead with the control problem? And I guess this is coming from the way that I've thought about this problem, to say like, I'm going to figure out the best way to control resources to access flexibility. And then given my controller, I can estimate the flexibility available through my controller, which is a combination of the availability of the devices, the capabilities of the controller, and the network. And then do you get to the same point eventually? Or are you going to be, is one inherently better or worse? Or are there just trade-offs?
Yeah, I think from the bottom up approach, something that we have to be careful is how to take the network constraint into consideration, right? So yeah, I think the approach I'm taking is mainly to make sure that we have the network constraint taken care of. I think there are also some bottom-up approach, for instance, I guess there are a lot of work early in the days by PNL and some others on the Minkowski sum of the flexibility region, right? If you have a homogeneous DR devices, you can just take their Minkowski sum of their individual flexibility that gives you the aggregate flexibility. But one problem with that is it's network agnostic. So you're not taking the network constraints in this problem. So I think if you have bottom-up approach that also takes into the network constraint into consideration, that could also work.
I think we're at time, so let's thank the speaker.
Thank you.
Yeah. Thank you for the questions.
Yeah, I'm gonna use it.